Hello student, welcome to uh, this class in which I am going to discuss operators. This part of the lecture is completely optional. This is not going to be included any kind of tutorials or uh, in any kind of examination like quizzes or NSEM, but this is an important concept which I feel that one needs to learn when you talk about quantum mechanics. Okay, so that's why I decided to provide this optional video about operators. Okay, so let's see what we are going to discuss in this class. So there's a very important question that we would like to address: how the average values of momentum or position or any other parameters will evolve with time in the general state. Okay, so this is what we are going to address. So before we come to this main question, we have to introduce several new concepts. So let's start one by one. Okay, so first concept is the commutator. Okay, so let's say if O1 and O2 are the two operators, let's say these are the two operators O1 and O2, then let's say we have to assign some known things to these operators. So let's say O1 is equal to X and O2 is equal to X squared. Now if I take the product of the O1 with O2, then what I will get X times X squared. So this will be my X cube kind of. Or when I take the product of O2 with O1, remember the order matters here. So in this case O1 is in the left, O2 is in the right, and here O2 is in the left and O1 is in the right. Okay, so if these are the two different let's say the product of the two operators, what I'm going to get, I'm going to get the same value, x cube here, x cube here. Okay, and if I take the difference means O1 O2 minus O2 O1, this will come out to be 0. Okay, another choice we can take, let's say O1 is equal to X, and now O2 is a differential operator, d over dx. In this case, if I take O1 O2, first O1 then O2, then I will get x times d over dx, whereas when I will take O2 times O1, then I will get d over dx times x. And in this case it is apparent to you that O1 minus O2 minus O2 O1 O2 minus O2 O1 is not equal to 0. Okay, so you have seen that it depends on the choice of the operators. Sometime this quantity we are going to define in a moment, this quantity is 0, and sometime this quantity is not 0. Okay, so that's what we have seen. Okay, so now we know that operators needs to operate on the wave function. So now we can say that, let's say psi of x is equal to x. Now we are going to introduce a wave function now, because these operators operates on some kind of wave function. So let's introduce a psi of x, and then under these conditions we know that O1 O2 minus O2 O1 times psi of x. Okay, so this is O1 times O2, which I have written here. This is minus O2 times O1, this is I have written here, and the value of the psi x, which is assigned as x, is written here. And if you do the operations, okay, and by using this whatever product rule, then it's easy to show that it will be some kind of minus x. Okay, so again that's what we have to even more emphasize, that this quantity is non-zero. Okay, now we know that momentum operator is written as minus I h cross d over dx. Kinetic energy operators is written as minus h cross square over 2m d2 over dx2, and this is energy operator is written as I h cross d over dt. Okay, so now this is a definition. So let's say if O1 and O2 are the two operators, then commutator, which is defined as this bracket, big bracket, O1 comma O2 big bracket close, is equal to O1 times O2 minus O2 times O1, and this is the definition of a commutator of operators. Okay, so you need to have two operators, and the commutator of these operators O1, O2 is defined into this fashion. Okay. Now we can take some examples. So for example, we can take X operator and P operator and let's evaluate its commutator. Okay, so this is the commutator. So the commutator is denoted by these brackets. Okay, so we know that when X operates on any wave function psi, it will give you X times psi, and when P operates on any wave function, then this is your position this is your momentum operator. Okay, now when we would like to evaluate the commutator of this X with P, okay, then we can expand this, so it will be xp times psi will go inside, minus px times psi. Okay, now I know what is the operator P here. So P is minus IH cross d over dx. So this is minus IH cross d over dx, and psi is taken here. Okay, now minus P times, now I can take this first because the operations are preferred in an order way. So first X will go with psi. So this is what I have done it. Okay, now by using what you say, this chain rule, okay, so what I can do, I can write down on my what you say value of P here, so which is minus IH cross d over dx. So this is what I have written, and this X I can take it out here, okay, because IH cross is a constant, so it does not affect the order, and X I have substituted here. Okay, and now it is clear to you, this will be IH cross psi. Okay, that you can verify it. So what we have obtained, the commutator of X with P is IH cross, because psi is common in both hand sides. So this is what we have obtained. Okay, so this is what I have said it to you. So then it is clear that X with P, or more specifically X with Px is IH cross. So the commutator of X with Px is IH cross. Okay, so observables belonging to non-commutating operators cannot be measured with unlimited precision. Okay, so this is what is the quantum mechanical statement, that those observables or those operators which are not commuting with each other. So you can see that this is non-zero value here, so we can say that X is not commuting with P, and under these circumstances these observables cannot be observable associated with these operators cannot be measured with unlimited precision. So now these kind of statements give you some kind of connection with uncertainty principle, where we talked about unlimited precision. Okay, so on the other hand, those observables which belongs to the commutating operator, so let's say X with X will commute, P with P will commute. Okay, we will see in a moment what kind of other operators we are talking about, what kind of other commutating operators we are talking about. So if observables are associated with the operators which are commuting with each other, then these observables can be measured simultaneously with unlimited precision. Okay, so now the measurement and the unlimited precisions are associated with the value of these commutators. Okay, so whether your operators are commuting or your operators are not commuting, this is an important and the correct statement. Okay, so now, as I said, that this is related to Heisenberg uncertainty principle, and Heisenberg uncertainty relation involves not commuting operators because there is a upper cutoff with the unlimited precision in the measurement. Okay, so now this is what I have said it. So now this is the generalized statement of uncertainty relation, and this is the what I could call as a correct way to describe the Heisenberg uncertainty principle. What we have done it was more like a hand waving, but this is a more appropriate way, this is a correct quantum mechanical description of the Heisenberg uncertainty principle. So let's say you have a two operator, O1 and O2, and now you take the standard deviation of O1 and O2. It will be greater than or equal to half modulus of average value of C. And now what are these O1 and O2? So O1 and O2 are non-commuting operator and their value is C. Okay, so this sets the upper cutoff in the unlimited measurement or the precision, unlimited precision while measuring these two observables or observables associated with these two operators simultaneously. Okay, so this is the correct statement. So if there are two operators and O1 and O2 and their value of the commutator is C, then uncertainty principle says that the delta O1 times delta O2 must be greater than or equal to half times the average value of C modulus. Okay, so this is the correct one. So now we know that from the previous slide that XP is IH cross. Now I can write down my delta X delta PX must be greater than or equal to H cross over 2. You see, this modulus is taken care by this one. Okay, so this is what is the correct statement what you have seen in earlier classes, but the origin of this uncertainty principle is coming from the commutator of the operators. Okay, now this is what we have seen. Now this is the first homework. Instead of taking the first power of x, if you take the nth power of x, you can evaluate this commutator value. Okay, similarly you can take the nth power of p, you can estimate this what it comes out. So these are the two small homework that you can do it if you would like to practice more about the commutator. Okay, now there are some properties. So what we are going to discuss in this slide, properties of commutators. So let's say these are the two operators a and b. So if I take the commutator of a with b, then this is equal to minus times b with a. Okay, these are simple things that you can verify. Now if you take the commutator of a with b plus c, then this is equal to ab plus ac, because this I can do the linear expansion and this will come out. Okay, now if I have a commutator of a with the product of the bc, remember orders matter. Okay, then it will be equal to first the commutator of a with b times c plus commutator of the operator b times commutator of a and a with c. Okay, this is the third property. Now the fourth property, this is the cyclic property based on this one and these two relation, that you can show that a with bc, b with ca and c with ab is equal to 0. Okay, this you can verify using third one and the first one, that this cyclic relation fulfills. Okay, this is similar like what might you have seen for the vector identity. Okay, now this is a new concept that I'm going to discuss in a moment in the next slide. So if you take the two operators a with b and you take the kind of some dagger which is adjoint, it will be equal to b dagger a dagger. Okay, the commutator of b dagger with a dagger. Okay, so as I said that if a and b, the commutator of a with b is 0, then it is said that a is commuting with b. Okay, and if a is commuting with b, then it has one more consequence, that the psi is an eigenfunction of a. If psi is an eigenfunction of a, then psi is also eigenfunction of b. This is the statements. Okay, so because if two operators are commuting with each other, they possess the common eigenfunctions. Okay, so this is another statement. Now to give you some more insight about this one, let me take a very simple example. So let's say this is a complex matrix. Okay, where I have a -1, 2, -1 as a diagonal element, and in the off diagonal element I have a -2i and +2i. Okay, so this makes you that this is a complex matrix. Okay, now what I can do, I can calculate the cofactor of matrix. I'm sure you have done it numerous times, how to estimate the cofactor of a. So if I want to take the cofactor of -1, then what I have to do, this will be my cofactor. Okay, so in this way I can estimate the cofactor of the whole matrix. Okay, and you know how it will come. It will come with the plus sign, minus sign, plus sign, minus plus minus, plus minus plus. So these are the cofactors I have written. You can do it or you can verify it. Okay, and once I have done the cofactors of a, then this comes out to be this one with the proper sign. So it will be -2, 0, -4i, 0, -3, 0, 4i, 0, -2. Okay, so this is a cofactor matrix of this matrix A. Okay, now I can take a transpose. What it mean by the transpose? I have to exchange the result. So what I will, so the diagonal remains as it is, -4 pi comes here, 4 and +4 pi goes here. Okay, and these are the values 0, so these are going to be unaffected. Okay, so I have taken the transpose of this cofactor matrix of A. So, and this is defined as an adjoint of a matrix. I'm sure you have seen it. Okay, and this adjoint is not a complex conjugate of that matrix. Remember, this is an important notion that you have to keep in your mind, that adjoint of a matrix is not equal to the complex conjugate of a matrix. These are the two different identity. Okay, that's what I have said it. Okay, so once you have obtained the adjoint of a matrix, okay, what you have to do, the inverse of a matrix is defined as adjoint of a matrix divided by determinant of A. That's how you have defined it. So now I can rearrange the term, and then I can show that the A inverse A is equal to I identity. This is always hold. So and from here it comes out that A dagger is equal to determinant of A. Okay. So now if A dagger is A, then A is known as a self-adjoint or Hermitian adjoint. These are the definitions that you have learned during the matrix manipulation and matrix multiplication and determinations of this thing. So if A dagger is equal to A, then A is known as a self-adjoint, or it's also known as a Hermitian adjoint. Okay, so if you take the product of the two matrices A and B and take the whole inverse of this thing, it will be B inverse A inverse. Similarly, what we have done, because your adjoints are related somehow with the inverse of a matrix, so it's easy to show that A with B, and you take the commutator and you take the transpose, it will be B dagger A dagger. Okay, this is the property that I have discussed last to last slide, and now I have given you a detail what is the meaning of the adjoint and how it is related. Okay, so now let's develop some more concept related to the operators. So suppose I would like to take the expectation value of this operator O. It is defined as psi dagger O psi dx integrated over entire space, and now because operator the order matters, so I have taken the O psi together. Okay, and under the condition that your psi is normalized, so there is nothing to divide. Okay, so this is the definition of your expectation value of your operator. Okay, now what I'm going to define, okay, let's say there is another operator O dagger, which is some kind of adjoint, which gives you the same expectation value of the operator, but the operation is performed into this following fashion. So what I have written, O dagger psi whole star times psi dx will yield me the same expectation value O. Then what I can conclude, that O dagger is an Hermitian conjugate of O, or O dagger is an adjoint of this operator O. Okay, so it means that so it means that because this side and this side is same, so now I can say that this value and this value is also same, and moreover, because now it is a self-adjoint, or this is my Hermitian conjugate from the previous slide, then O dagger will be O, then this is the definition. Okay, so this is the way that I can conclude, and it has one more consequence, that this estimate that O dagger is O. Okay, so what I have said, there is an operator O which expectation value is defined as this way. Now if I say that if there is another operator O dagger which yield the same expectation value by performing this way the operation, then I can say that O dagger is an Hermitian conjugate or the adjoint of O. Okay, and because of this, then O dagger will be O, and then I can say that O dagger is O. Okay, then O is known as a Hermitian operator, or it's also known as a self-adjoint operator. Okay, now let's say this is my operator d over dx, and let's check whether this is an self-adjoint or not, or Hermitian operator or not, or what is the Hermitian operator corresponding to this operator. Okay, so as I define, my O is this one, so I can write psi dagger O psi dx. Okay, integral. I have replaced or substituted the value of O, what I have defined it here. Now this is the one definition. So this is what I have written. Now let's do the integration by part. Okay, so I'm going to do the integration by part. So when I do the first time, what I will get psi star psi, because this will take out. It goes minus infinity to plus infinity. Okay, now minus, this will be the second part. So integral d over d psi and then integral of this. So first differentiation, so integral, first differentiation, then integral, so this will yield me this one. Okay, now it's easy to show that this psi star psi will go to 0. Okay, then what is left? I am left with this minus times integral of d psi star over dx times dx. Okay, now this is what I have got it. Okay, now what I can do, I can take this minus sign inside. So I have taken this minus sign inside, and this is what I have written. Okay, now this is my operator. D over dx is an operator. So now what I can define, minus d over dx is my O dagger. And then it is easy to show that O dagger psi whole star is this one times psi. So then it is straightforward to show that the conjugate of d over dx is minus d over dx. So d over dx and minus d over dx are the Hermitian conjugate with each other. Okay, so now this is another operator, let's say the momentum operator. And if we do this another example, so we can say that p psi dagger. So this is my p psi dagger. I can take this IH cross out, and when I'm taking the complex conjugate, then this will become minus I to minus I, and minus minus I will be plus. So this IH cross is taken here. Now what I have left with, I have left with d over dx times psi, and star is as it is because I have only taken this prefactor times this. Okay, and this I know how it will be. So now I can take the integration over part, and then psi goes to 0 as x goes to 0. Then we can rewrite this part. You remember, this is what I have written here. This is what it's supposed to be from the earlier definition, that if your operator is here, and from this one I can say that this is what it comes out to be, this one. Then it is evident that psi star times p psi dx is going to be this one. So then it is clear that when I started this one, I have arrived this one, then my this operator is a self-adjoint. Okay, so the p dagger is p. It's also easy to show that your x dagger is x. Hamiltonian is always a self-adjoint. I dagger is minus I, and d over dx dagger is minus d over dx. So the adjoint is different than the complex conjugate. Okay, now the eigenvalues of an Hermitian operator, eigenvalue of Hermitian operators are real. Okay, so let's, O is an Hermitian operator, then O psi is equal to O, where O is an eigenvalue of this operator for this eigenfunction. Okay, and now to show that this is a real, so this is the definition of your Hermitian operator. O psi star psi dx. Now O will operate on here, so this will give me small o. This is small o I have taken. Now I can take this star inside, so O star will come out here, psi star psi dx, this one. Okay, now this is another definition of the same quantity here. This is written in a another way. So psi star O psi, now I know what is my O, so it will give me O, so I have taken here. So now these both are the definition of your expectation value of O, so means that these are the two quantities same. This integral is identical in both equation. It means that O dagger is O. It means that the eigenvalues are real for a Hermitian operator. Okay, so this we have shown that eigenvalues of Hermitian operator, where Hermitian operator in this case is O, are real. Okay, so these are position operator, momentum operator, this is your kinetic energy operator, these are your Hamiltonian, and all are Hermitian operators. Okay, and their expectation values are real, so they have a real eigenvalue or real observable. Okay, now this is a statement. Operators representing all dynamical variables, momentum, position, energy, and so on, must be Hermitian. So all the operators which corresponds to dynamical variables must be Hermitian. So their eigenvalues are real. Such dynamical variables are also called observables in quantum mechanics, because in reality or in nature you always measure or observe the real things, not complex things. Okay, so that's why, because you are measuring in nature momentum, position, energy of a particle, and they have to real, so their operator has to be Hermitian and their eigenvalues have to be real, and these observables are known as these dynamical variables are known as observables in quantum physics. Okay, now this is something important. Now what I'm going to do is unfazed theorem. Okay, so what the unfazed theorem is saying, before I go to the statement, this is what we have discussed in previous slides, but let me again state it. Suppose there are two operators A and B and both are commuting, so means the commutator of A with B is 0. Then what it means that if psi is an eigenfunction of A, then psi is also eigenfunction of B, means A and B possess the common eigenfunction. Okay. Now if I take the operator A with the Hamiltonian and it goes to the 0, if this commutator is 0, then what I can say that the stationary states of or the eigenstates of this Hamiltonian are also the eigenstates of this Hamiltonian A. Okay, because A is commuting with H, which is same as here. So all the stationary states are the eigenstates of your Hamiltonian are also the eigenstates of your A. Okay, in other words, states of definite energy, okay, because the eigenstates of these Hamiltonians are the states of definite energy, are also states of a definite parameter, are definite observable represented by A, by assuming that A is your Hermitian operator. Okay. Now if A has no explicit time dependence, so A is a time independent variable, for example momentum operator, then what the Unfest theorem says that if you take the time derivative of the expectation value of A, it will be minus I over h cross expectation value of the commutator of A with H plus dA over dt of the expectation value. Okay, and since my A is time independent, so this term will go to 0. So for time independent operator, this is the statement of your Unfest theorem. The derivation of this statement I will provide in a handwritten notes as a supplementary material. If you are interested to know how this comes out, it is just a few lines, a simple derivation. Okay, so this is the statement of your Unfest theorem, and it has a very important consequence in quantum mechanics, and this is the theorem which connects the quantum world with the classical world, which you will see in a moment. Okay, so now it is easy to see that the parameters, physical parameters, or the observable remains constant if this is 0 over time. If this is 0, means that A with H, if this is quantity is 0, it means that d of expectation value of A with respect to t is 0, means the average value of A is constant over time if it commutes with Hamiltonian. Okay. Okay. Now A with H, commutator of A with H is 0 would not only imply consistency of a parameter, but also that is a definite in that state, definite in the state. Okay, so let's see the application. So the one application we are going to do is something related to the particle in a box. So this is the wave function for a particle in a box, infinite box. This is your normalization constant, and this is your wave function for the nth state. Okay, so we know that this state, this function is an eigenfunction of Hamiltonian, but this is not the eigenfunction of P that we have seen in the earlier videos. Okay, this can be verified as, okay, so let's say you are taking the commutator of P with H, okay, and then you are operating with this wave function or eigenfunction. So we can open this P with H. What will you will get? You will get PH minus HP, and so I got PH times phi n minus HP times phi n, which is non-zero. Okay, that you can show it. However, on the other hand, if you take the first commutator of P with H, okay, and now you take the expectation value, then what you will get? Expectation value of any quantity is phi star expectation value of this operator. So suppose you treat this operator times phi n, and this is 0 because you know this P commutes with Hamiltonian, and from your Unfest theorem this shows that this is 0. Okay, so this 0 means this you can show it by hand. I mean, this is the steps that we have done it. So PH here means you have to open this PH minus HP. Okay, so now there are two terms. So this is the first term I have written, and this bracket doesn't mean anything. It's just to take dx out. This is nothing related to the commutator. So what you will get, phi n star PH phi n. That is the first thing I have got, and this is what I have got, minus h phi n star HP phi n. Now you know h, when h operates with phi n, what it will give you? It will give you en phi n. Now en is not dependent on x. I can take it out from the integral. So this is what I have taken. Okay. Now the second term is a little bit interesting. So what I have written second term is phi n star hp phi n dx, let it be dx. Okay. Now this part, because h is my Hermitian operator, this part I can always write as a h phi n whole star. You have seen when we talk about the Hermitian operator, that was the whole purpose to introduce this. I have clubbed it together, and rest of the things as it is. Now h commute with, and what is the this one? From this one it will be en phi n. This en is a real quantity for a particle in a box, so star will not make any impact. So this is I have written. So now I can take en, and then phi n will become phi n star p. So now in both things you got en out. I can take the en out, and this is the identical what you got. So this is 0. So from the Unfresh theorem, if you take the time derivative of the average value of the momentum, it is 0. So it means that momentum is a constant of motion. Okay. So till now we have discussed when particle is not experience any force. Okay. What about when particle experience a force? Consider a harmonic oscillator. So this is our definition of your Unfresh theorem. Okay. Now if I take my A as a P, then this is what will be based on Unfresh theorem, that d over dt of expectation value of P is equal to minus I over h cross P with h. Okay. And now instead of a particle in a box, what I'm going to consider, particle experience a force, and this force is related to the potential associated with the harmonic oscillator. So now my Hamiltonian is p square over 2m plus half m omega square x square. So when I substitute the value of h here, I have to evaluate this quantity. Okay, so I can evaluate this quantity. So let's say h p with h, that's what it here. I have written my value of h here, so then will be two terms based on the this chain rule. 1 over 2m is common, so a commutator of p with p square, you know this will be 0, you can verify it here. And now half m omega square expectation, well, commutator of p with x square. You remember that I have given you an exercise, evaluate the commutator of x to the power n times p. Okay. Now instead of this one I have reversed the order, so I will get minus sign, and if you do it everything correctly, this is the value of this one. What we have seen x with p, that was IH cross, so here is minus IH cross, and when you take this one you will get 2 IH cross. So what I got after substituting this value, okay, this 2 and this 2 will cancel out. Okay, so what I got, minus IH cross m omega square and the operator as x here. Okay, so this is what I have got. Okay, this is what the definition of your what you say from the Unfresh theorem. This was the value here. If I substitute this value here, then this prefactor will cancel it out, and what I got minus m omega square expectation value of x here. So if I take this one, this is what it comes out, and if you can notice what it looks like, this is nothing but, if you take this derivative, it is proportional to the minus of the expectation value of the x, which is minus of the displacement. This is the Hooke's law for harmonic oscillator. This is equivalent to the force, and this is equivalent to the minus of the displacement. Okay, so what you have established, that when you satisfy or when you follow the Unfresh theorem, which talks about how the expectation value of an operator evolved with time, okay, it gives you something, and this is equivalent to the findings what you have seen in the classical world. So Unfresh theorem is a connecting point which connects your quantum observables with the classical findings. It means that when you take the average of any variables or any operator, then it has equivalent meaning in the classical world. Okay, so this is in general, you can show it by yourself, that if you take dp over d of dt of the expectation value of p, then this is equal to minus of expectation value of dv over dx. So this is one of the simple example of this is statement, but this is the general statement. Okay, so the Unfresh theorem is the connecting point between the classical world and quantum world, and this says that average value is the one which is related to the classical world, not the other way around. Okay, so I hope that you have got some additional knowledge about the operators, in which we have discussed what are the commutators, some more properties of the Hermitian operators, real eigenvalues associated with the Hermitian operators, and at the end of the day is the unphased theorem. The derivation of the unphased theorem is not complicated, which is provided another additional material which I have not discussed. Okay, so thank you very much.